Okay, so welcome to week 8 of Electromagnetics in Guided and Wireless Media course. The course being offered on NPTEL portal, and the course instructor is Professor Pradeep Kumar from IIT Kanpur. I'm Shazam Bhatt, and I'm a PG student at TU Berlin and Paul Drude Institute, and also a part of IIT Bombay. And I'm the coordinator of this course, and this is the final week of this course. We are into the final week, and it's been a very sort of enjoying journey till now to basically understand the phenomena of propagation of electromagnetic waves in uh, certain guided mediums like waveguides and also certain wireless media. And now today we are going a little bit different towards the optics side, which is also an electromagnetics wave, but for the week 8, you might have studied about maybe lasers, which is basically goes into the optical frequencies. Okay, and but at the end it's an electromagnetic wave, and you might have studied about the laser properties like the coherence of the electromagnetic wave, the directionality. And then you might have studied about the laser pulses, maybe the Gaussian pulses, the laser beam as a sort of a Gaussian Gaussian spot. You might have briefly talked about maybe transforms. Which transforms are we talking about? A Fourier transform going from a time domain to the frequency domain, or going from a real space to the case space representation. So these are the two Fourier transforms which we mainly deal with. And that means you go from a second, if you talk about in terms of dimensions, you go from second to basically hertz, which is basically per second, or you go from let's say meter to inverse of meter, which is basically the inverse space representation of the Fourier in the Fourier transform. So these are really important things, even mathematically talking. These are all mathematical formulations. And then you might have talked about maybe diffraction. You might have talked about interference. And these are the wave phenomena. We are treating the light, we are treating the electromagnetic wave because it's a wave. So obviously it's going to show certain wave phenomena which are dominant with these electromagnetic waves or any of the waves, diffraction and interference effects. So today what we are going to see is basically solve again the questions, and wherever it's required we can basically discuss more about the essence of those questions. Okay, so let's get started with the first question itself. And we're going to discuss a little bit about these questions because most of them are theoretical questions, uh, except one, two, three, four, five. Five questions are theoretical, five questions are numerical. So in the week 8, you have five questions are a little bit theoretical, but it needs under mathematical understanding, but five questions are like numerical solving questions. But we're going to revise the concepts using these questions. So the first question itself is basically says that the first question the first question itself says that if you have, let's say, a laser beam is different from an ordinary light beam due to its. Now, first of all, what is a laser beam? What is the ordinary light, and how it differs from the ordinary light? So, if you talk about a laser, and if you talk about the ordinary light, I won't talk in terms of the mathematics. I will talk briefly in terms of the conceptual understanding. Maybe we can also look into the mathematics. But essentially, how the ordinary light is produced, you have certain, let's say, if you have a semiconductor, and it has energy levels. We call the bottom of the we call the bottom of, I should say, conduction band as EC, and we call the top of valence band as EV. Okay, so this is in space. So this is X and this is E. This is called as band diagram. You might have also heard about band structure. So the band structure is exactly E versus K. So it's actually a dispersion relation. So so band structure is you plot K here, you plot E here. So essentially the band structure is the transform, the Fourier transform of real space to inverse space. So that's basically what band structure is. So you go from meter to per meter. Okay, so that's what when you see the band structure, you might have something like, if this is E as a function of K, this is K. You might have seen something like this if it's a direct band gap, and then the top of this we call as valence band, the bottom of this we call as conduction band, and this gives the energy gap. And there are other bands also depending upon how the structure, how the material is. And this point is called as gamma point. It's the high symmetry point. And what does it refer to? If you have a crystal which looks something like this, let's say you have a crystal which looks something like, not exactly like this, then it's a three-dimensional crystal. Then you select a point which is in the center. This is basically gamma point. If you go in this direction, this is some other point, X point. You go in this direction, this can be M point, R point, so on and so forth. So these are different Miller indices or the direction indices in the crystal. So essentially, if this is, let's say, gamma point, then this is basically an X point. So you are going from gamma to X direction, your band structure is going to change. So energy of the electron is going to change. So it's basically how the energy of an electron is in K space in different directions inside the crystal. That's as simple as that. Now, now you know that whenever you have, let's say you shine, you irradiate certain, you irradiate, or maybe not irradiate, because in this case we want some light. We want to understand how ordinary light is produced. Then basically what happens is that if you apply certain voltage to a device, the electrons are getting excited. The electrons get excited to different energy levels, and essentially the electrons come back, recombine with the hole. So there is recombination, and that recombination basically leads to the generation of the photons. So you that is the ordinary light scenario. And now what is basically happening? If you have, let's say, applied some potential, the electron goes to higher energy. So there are a lot of energy states present. Okay, so this is the bottom of conduction band, this is top of valence band. You applied certain potential. So essentially what is going to happen when you apply the potential, let's say, if you have applied positive here, you have applied negative here, positive will bring the bands down because it reduces the electron's potential energy, and negative brings up the electron's potential energy. So the bands go like this. So bands have a certain slope, and now this is the direction of the electric field. Okay, and this is conduction band, this is valence band, and now the electrons are gone here. These are the electrons, okay, in different energy states. And essentially because there's a slope, so electron will like to go down slope. Okay, and once it goes down the slope, it also recombines. So electron goes here, then it goes down here, goes down, and every step it takes down is it's losing energy, and the energy is given basically to certain other systems. It can be given to the lattice, it can be given to certain other, I should say, systems, certain other quasi-particles. So essentially, once the electron loses energy, it gives this part of the energy to something called as phonons, which is basically heat most of the time. Okay, so it releases it in the form of a heat, is basically absorbed by the lattice, and the lattice starts to heat up. But once it is transitioning like this, the electron also transitions, or it recombines back with the hole. So there's a hole over here. So So the concentration of electron is equivalent to concentration of holes. We are assuming it. So as many the number of electrons in conduction band will be equal to the number of holes in the valence band. So once it's losing energy, it also recombines. So the recombination process naturally occurs. And once it recombines, it releases the energy in the form of photons. And that energy is exactly the energy gap difference, at least theoretically, not experimentally. So you have a photon, and essentially there are so many electrons, so many recombinations are occurring, and so many photons are basically released. Okay, now what is the difference here? This recombination, which is basically taking place, it is by something called as it's a natural decay of the electron. It's a natural decay process, something called as spontaneous recombination. Spontaneous recombination means it happens by its own. I mean, it's a very crude way to say it, but it happens by its own because electron is in the higher energy state. It wants to come to the lower energy state, and while it comes, it recombines with the hole and releases the extra energy in the form of a photon. That is the basic idea of a spontaneous recombination. And once these photons are released, this is basically what gives rise to electromagnetic wave, or the light that's basically coming out from the, I should say, from the LED source, or from the laser, not from the laser, from the LED source, or from a thermal lamp. But it's not the same thing. It's not the same light that's coming out from a laser. There's a difference. So that's the essential idea I'm trying to highlight. Now, once it generates these photons, the essential thing is that these photons are randomly generated. When I say randomly, that means each of the photon doesn't have any phase relationship. Okay, so if say one photon is released like this, so essentially the electromagnetic waves are generated, but all of the photons or all of the electromagnetic waves are not in phase with each other. So they are out of phase with each other. Okay, and there is no directionality. So let's say the one photon was released in this direction, another was like this, another was like this. So it's all sort of a messed up process that gives rise to this sort of a light, which is basically called as light generated from the spontaneous recombination. And this is the most of the light sources you have around you. Okay. And now what is essentially happening in the laser? In the laser you have additional level. Okay. It's consider it like energy levels. Let's say this is energy level 1, this is energy level 3, and this is energy level 2. What basically happens is you excite the electrons from this region to this region, and you populate it, and then it naturally decays to this region, to the second energy level. So this is fast, okay, fast recombination or fast decay, okay, and it gets accumulated here. The electrons get accumulated here. And finally it decays back, but this decay is slow, okay? And once it does, this decay, the natural decay will occur, but this natural decay is slow. And in order to bring these photons in order to bring these electrons down, you supply with some external stimulus to bring all of these electrons down simultaneously, all together. Once they come down and recombine with the holes, they release the photons simultaneously, all in phase. All in phase. So it's as if the electromagnetic waves are released like this, like this, like this, like this, all in phase, and they add up and they give rise to a coherent electromagnetic radiation that's coming out from this particular system. That is the essence of the laser. So that's why this recombination, this is called as stimulated emission, rather than a spontaneous emission or a spontaneous recombination, whatever recombination or emission, it gives rise to the same process. So this was spontaneous emission, This is sorry, this is spontaneous emission, this is stimulated emission. Why? Because you are stimulating it with the external stimulus. And this external stimulus can be another light source, or it can be another electric field source, or it can be any other source, which is basically supplying the energy to the system. It can also be heat. So this is the essence of the laser. Now, once you have all of these photons in the phase, they basically have certain directionality also, and they add up all of the phases and they stay coherent. And now you have a beam of light which is basically going in certain direction, in which the electromagnetic waves are all in phase, and you can do all sorts of cool stuff with this. And you also have now basically directed most of the power of these photons in a particular direction. So most of the power of these photons go in this particular direction. So you have the power directionality. Okay, your power doesn't go here or here. You have a directionality of the power in the laser beam. Okay, so that is the essential concept of this particular. Now there are detailed things about it. This is just a layman picture of what basically happens. So you have spontaneous emission, you have stimulated emission, and essentially this gives rise to this something called as lasing phenomena. Okay, now so the answer to this question will be coherence. It's because laser beam is coherent, it's directional, and monochromaticity is also important. What is monochromaticity? Is that uh, if you talk about monochromaticity, mono means single, chromatic means the color, so it's basically a single wavelength emitted. Okay, so essentially the light coming out of, if you draw the energy versus wavelength of this, it will be something like this. It will be very sharp. So this line width, the line width is very small. It means delta lambda is small. Okay, it's a monochromatic source. That means it contains only single wavelength, or at least it's peaked around a single wavelength. Apart from this, if you look at the spectrum of the this light source, let's say a thermal light source, which is emitted by a spontaneous emission, it will be something like a black body spectrum. So the entire spectrum will be emitted. So you have a lower wavelength, then you have a higher wavelength. So the entire spectrum is basically emitted instead of a single monochromatic source. So that's why if you see your even your normal thermal lamps, you have a whole range of colors that are basically being emitted. And even if you have LEDs can they also emit a whole range of spectrum of light. And why that happens, it has different reasons. We don't want to go into that reasons right now, but this is essentially important. That's why you see most of the time you see a laser that is only emitting a red color. You see a green laser that's only emitting a green color. So the essential fact is because they are monochromatic, because there is no other, they are not polychromatic. Okay. Now you can do certain things to make it a polychromatic, but that's not the essential thing. But the main question is that you have a laser that is monochromatic, which essentially emits a single wavelength. And this line width is pretty much smaller in the laser. Now it depends upon other factors also, but this is the essential concept. So this is the exact answer of this question. So you have all of these as the answer of this question. So the answer is all of these. Okay. Now the output from a single mode fiber operating at helium neon is approximately Gaussian with a beam waist of 5 microns, the corresponding divergence. So if we talk about a single mode fiber, and if you have a fiber and if you feed it with a helium neon laser that emits around 633 nanometers of wavelength. Okay, it's a helium neon laser. So you basically have helium and neon atoms and you are exciting those atoms and they are emitting the coherent radiation. So the output is approximately Gaussian with the beam waist of 5 microns. So what is this beam waist now? If you talk about what is this beam waist, so you have essentially a Gaussian beam that is basically propagating. This is exactly what is referred to as the beam or Gaussian beam. It's sort of it diverges. Okay, so the corresponding divergence we need to calculate this corresponding divergence. Okay, so how are we going to do it? So the essential concept is if you have, let's say, a Gaussian beam that is propagating, it will have certain divergence, which is basically this angle, the angle at which it is basically diverging. And it also has one more parameter that is something called as it's called as Rayleigh range. I think there's a question on Rayleigh range also. So the Rayleigh range it defines the distance from, I should say, the beam waist over which the cross section of the laser beam doubles. Okay, and and so basically this is used to characterize that I should say how quickly the beam diverges as it propagates through the space. Okay, so how quickly divergence is taking place. It also is measured by this Rayleigh range. We'll talk about Rayleigh range more in the next upcoming questions. But essentially, the fact is that if you have a Gaussian beam, then you have this width of this Gaussian beam, let's say W naught. Then what is going to happen? The far field divergence angle, this particular angle can be written in terms of wavelength, which is lambda over pi W naught. Okay. Okay. And where this W naught is basically the beam waist. And if you are given the wavelength as 632.8 nanometers divided by pi into beam waist is given as 5 into 10 to the power minus 6. So this will be 632.8 into 10 to the power minus 9 divided by pi into 5 into 10 to the power minus 6. So essentially you get theta in terms of radians, which is 0.0403 radians. And you can convert it into degrees and you get around 2.31 degrees as the answer of this question. So what is basically says that this particular divergence will be around 2.31 degrees. So that's the essential concept of this particular question. And it also happens like if you are trying to, let's say, if you have a lens system, if you are trying to focus in with the lens, if you're trying to focus this laser beam with the lens, it's going to focus at this particular point, which is basically the focal length of the lens, and then it's gonna diverge also. Okay, so it depends upon this how better you place your let's say you want to measure certain sample, how better you place it at the focus. Otherwise you're gonna place it, let's say, at certain point which is basically a diverging point, and then the specific characteristics of the beam will be different. Okay, so essentially this is exactly going to be the beam width of I should say a beam waist of this particular Gaussian beam. Okay, so the concept is that once the laser beam is emitted, the profile of this beam, what do we mean by profile? We mean a spatial distribution of this beam, that how it is distributed in space. Okay, so it looks something like this. It's basically a Gaussian sort of profile. So if it's moving in this direction, let's say this is Z direction, then if you zoom at this Gaussian and if you draw it in XY domain, XY dimensions or XY coordinates, it's basically something like this. That means basically you are looking at this beam from this side. This is exactly how it looks. It looks like a circle. It's not, it looks like a circle, but the intensity is basically varying like this. So this is basically the maximum intensity of this laser beam. And as you go away from the center, the intensity drops because it's a Gaussian profile of the laser beam that's being emitted. Okay. And this is basically, if you look at these 2 points where the intensity drops to 1 by e square of the value, let's say the maximum value was I naught, which is basically this value, then the point where intensity drops to I naught by e square, it's something called as FWHM of this particular Gaussian beam. And most of the time, this is reported in the even if you see certain laser specification, they report the beam width of this particular Gaussian beam. And that means it's measured from point this to this. And most of the time, if you have let's say a most of the time if you have let's say a Heine laser with a Gaussian profile like this, the beam spot or this beam, the beam spot or the FWHM, it can be around maybe 1 mm. It can go down up to in micron regions also, micrometers. Okay, and the essential concept is that because let's say we considered a helium neon laser, that means it has a wavelength of 633 nanometers. That means the best you can do is let's say what you do is that whenever you have a incoming beam of laser which is having a Gaussian profile, and you have a lens, and the lens tries to focus it. Let's say this is the focal point. So essentially what you are doing at this point, you're shrinking this beam width. So you're shrinking this beam width. It becomes smaller now. Earlier it was like this, you are shrinking this beam width now. Okay? But how much you can shrink this beam depends upon obviously the wavelength, because you cannot go below the wavelength. You cannot shrink the wave below its wavelength. It doesn't make sense. Something called as diffraction limit. Okay, so essentially the concept is that if you have a Gaussian packet, and let me draw it like this. Let's say this is the lens in this direction. Let me draw it lens like this. And now you have a Gaussian beam packet coming in this direction. So this is a Gaussian packet coming. You want to focus it here. You want to focus it here. At this point, the Gaussian wave packet will be reduced. And let's assume the wavelength of this Gaussian packet was 633 nanometers. Okay, so that means the and this initially before the lens, this entire uh, beam width, let's say FWHM, was around uh, let's say double the wavelength. That means 633 multiplied by 2, 6, 6, 12. So let's say this was around 1.266 micron. Okay, that means there will be two wavelengths fitted inside. One, one, two. So this will be the exact representation. So the two of the wavelengths will exactly fit into this wave packet, and they are propagating into the towards the lens. Now once they hit the lens, now they're at this particular focus point, the the FWHM will be reduced. Now it will look something like this. It will look something like this. And the best you can focus is you can make this of the order of 633 nanometers. That means at least there will be one of the wavelengths, one of the I mean of the order of one wavelength. It can focus. You cannot go below. You cannot shrink it to a level of less than wavelength. Otherwise, it doesn't make sense, because if it doesn't have any even a single wavelength inside it, then you cannot do it. There are other ways. There are tricks people use to go below the diffraction limit, but that is a whole advanced level of a topic that goes into a different domain. But this is essentially the idea. That's why even if you shrink, you cannot shrink below down its wavelength, and that's the essential concept. And if you let's say now, why is this important? Because you want to image the nanostructures. If you want to image the nanostructure, that means you have made a let's say a transistor. If you made a transistor on a chip, let's say this is a chip, semiconductor chip, and you made a transistor, let's say a MOSFET. This is a MOSFET. And all of this is made with the help of lasers. Let's say you have a silicon substrate, then you have a mask which looks something like this. It's a mask that has a design. It's sort of it looks like a net, but it's called as mask. And then you irradiate with light source, and whatever the design is on the mask, it gets imprinted on the silicon. And as it does so, it produces these mini transistors, which are basically nanoscale devices, which are nanoscale devices. And how good or how smaller these features are depends upon your laser. Depends upon your laser. Okay. Let's say let's say you're for example, it's not exactly used like this, but I'm saying for the sake of understanding. Let's say you used a 633 nanometer laser here to irradiate on the mask and to make transistors. Then you cannot exactly make smaller transistors because your wavelength is 633 nanometers, and it's gonna imprint at the best or at the most the size of the nanostructure or the size of this particular small section that is basically imprinted will be of the order of wavelength. You cannot go below this. You cannot print the feature size below this. Now, what you do instead of using 633, you go to UV region, something called as deep UV lasers. You go to, let's say, maybe 200 nanometers, or you go to 100 nanometer, and you use the 100 nanometer laser to imprint these particular features, and as a result, your feature size reduces. Your feature size that you can print, that reduces. And the lower you go down, the better feature resolution you will have. Okay, it's as simple as that. It's as if you have a tap of water, and you have a bigger tap, and you have a smaller tap, you have a thinner tap, you have a thinner tap. The flow from here will be sharp. The flow from here will be sort of broadened. So essentially, if you want to make a small features, you're gonna use this particular tap of water, not this, because this is going to give you a large feature size. Okay, it's a very crude example, but it sort of simplifies it. And for making a very small feature size, small features in a on a nanostructure, you're gonna use this particular sharp water pipe in order to make certain sharp features on this. Okay, so that is what exactly the light does. And also in terms of imaging, if you want to, let's say, image certain nanostructures, your let's say your transistor, if let's say your transistor is 10 nanometers, then you're gonna need certain light source that is having the wavelength of the order of 10 nanometers. Otherwise, it's not gonna interact. Okay, it's not gonna interact. If even if you have, let's say, even if you have, if you talk about solid state devices or solid state physics, you have a crystal. I have talked about it in the first lecture. You have the solid state crystal, and the atoms are spaced at the lattice constant, which is of the order of, let's say, 5 angstrom. That means if you want to see these atoms in the crystal, your wavelength with which you are seeing it should be of the order of 5 angstrom. It should be near that. That's why you perform something called XRD, which is basically X-ray diffraction. Because X-ray we have a very small wavelength, and they are very high frequency electromagnetic waves. That is why it makes it, I should say, it makes us to see those particular atomic sites or atomic planes to be specific in the XRD measurements. And it essentially boils down to that fact. That's why these deep UV lasers and the research in these deep UV lasers is essential because it dictates how small features can you basically make on your chip or whatever you are using. Even if it's a chip, even if it's a transistors, if you want to make your microprocessor is basically something like this. It's maybe a 2 inch by 2 inch sort of a structure, and it has around nowadays 50 billion plus transistors. How is it possible? It's only possible if you miniaturize the transistor and if you use certain feature size which is very, very, very small. Nowadays, the size of the transistor is of the order of maybe 40 nanometers or 20 nanometers. Okay, so in order to make these particular sizes, you're gonna essentially have require the wavelength of this particular order. So it's all dependent on how good your light source is basically. So that's why the research in the light source and producing essentially finite sized light sources or smaller or deep UV lasers is essential for a lot of applications even in electronics industries. So this is about what basically happens to the feature sizes and how why these Gaussian features are really important. Now moving on to the second question, moving on to the third question, we are talking about double slit interference arrangement. One of the slits is covered with a thin mica sheet whose refractive index is 1.58. The distance between the two slits is zero point 0.1. Separation between the slits is 50 centimeters. Due to introduction of mica sheet, the central fringe gets shifted by zero point 0.2. So essentially, you might be knowing about this famous double slit experiment, the Young's double slit experiment, and it is basically the starting point of most of the modern physics, to be honest. So you essentially have electromagnetic waves that are coming in. These are basically plane waves, and you know the important concept here is now because you have studied about the far field and the near field concepts. So the one of the important thing about the Young's double slit experiment is that you assume that the light source is coming from far away. Why? Because for when it's coming from far away, when it reaches near the slit, they almost behave as if they are plane waves. So the essential thing is that they should behave as plane waves, a sort of a monochromatic plane waves. And that means your light source is far away, and when the light source is emitting, it's emitting like this, then far away it becomes sort of a plane, and this curvature sort of goes away, and they become sort of a plane waves moving. If you do the Young's double slit experiment, and if you put the slit here, it's gonna show you a different thing because these waves will not be plane waves. It will be in a near field condition. That means your light source will be very close to the slits, and you no longer have the plane waves. You're not going to see the diffraction pattern at all. Okay, so that is very essential for the Young's double slit experiment, which is not mostly talked about in the books. And now you have these plane waves hitting. It hits these, I should say, slits. These are the slits, and you have the waves going through it, and you have the waves going through it. And now, because of these overlapping regions, you have something called as interference of the waves. And if you place a screen over here, what you're gonna see, ideally or theoretically, what you should have seen that this light would have reached here at this point, and this should have reached here at this point. So you should have ideally seen only two spots here. But that doesn't happen. What happens is basically you have a peak and then you have certain smaller peaks and you have something like this. So this is called the central fringe of in the double slit experiment. So you have a sort of a sink-like arrangement or a sink function. Basically, intensity, the intensity profile looks something like this. Okay, and it's in space. It's actually the spatial distribution of the intensity. The spatial distribution of the intensity. And I think we have talked about it a lot of times, even in high school physics, and even in lower classes, undergraduates. And one of the essential concepts here is why this is happening because you have interference, and you have interference in such a way that the intensity goes to maximum at this position, and you have this is a node, and there is an anti-node where the intensity drops to zero. So the intensity at these points drop to minimum. So you have destructive interference there. So you have destructive interference here. And at this point you have a constructive interference. Okay. And an essential thing is that's why you see a peak which is higher in intensity compared to other smaller peaks. Because what is basically happening is that there is energy redistributed. So whenever the destructive interference is happening, where is basically all the energy going? The energy cannot just sort of go away. So that all of that energy is basically going into this maximum peak. And that's why you see a maximum peak, and then all of the peaks get smaller and smaller. And wherever that destructive interference is happening, the energy goes into the constructive interference part. So energy is always conserved. It's not going to be destroyed altogether. Now, essential concept about this is, now what is basically done in this particular experiment. Let's say first what is given in the question. If you take this particular thing from here and you place it somewhere here and you take the details of the questions. Let me remove this. So what is given? You have the refractive index. There's a twist in this question, that there's a mica plate inserted here. A mica plate inserted here. So essentially, it's sort of a thin sheet that is basically inserted in front of the one slits. Now what it's gonna do, it's gonna introduce additional optical path difference. So optical path difference is gonna be introduced. Okay, and that means if let's say this is D, the distance between the slits and the screen, and the distance between the two slits is, let's say, small d, and the refractive index of mica is n, and then there is the thickness of this particular sheet is t, then the additional path difference that is going to be introduced will be something like n minus 1 times the thickness, which will be basically the refractive index times the thickness of this particular mica sheet. And why does this path difference come basically? And what happens because of this path difference? So essentially what is asked in the question, the central fringe gets shifted by 0.2 centimeter. So once you have this introduced in the double slit experiment, your central fringe will shift basically. It will no longer be at center. It will be shifted by some amount, which is basically given by 0.2 centimeters. Okay. So if you look even from the theoretical aspect, what basically happens is that the light coming from, let's say, this point to this point, and the light coming from this point to this point, the lower one has to basically travel the additional path, which is basically this. So this part and this part is same, except that there is an additional path difference for the lower slit. The light from the lower slit has to travel additional path difference, which is basically this. So the light comes here, the light comes here, but this light travels more travel because it has an additional path. Okay, so the additional path is basically encompassed as a phase in this particular light. So essentially for all of the points, you have the light coming like this, light coming like this. Then if there is a light coming here, you have a light coming here. So this path difference is there always. Now additionally, when you are going to insert a mica plate, thin mica plate, what is going to happen is that the light is going to still reach this particular screen essentially, but it's going to introduce additional path difference. Okay. And because the important thing is that you are not blocking the slit completely. And now if we try to solve this, the the shift in the shift, if you want to compute now the shift in the central fringe, this is basically the extra optical path difference that is introduced. But if you want to compute the shift in the central fringe, that will be, that is, let's call it x. It will be somehow dependent on this delta, which is basically the optical path difference, but then there will be the overall distance divided by the distance of these particular slits. That will be the exact shift of the central fringe, which is basically due to this placing of the mica. So the x will be something like n minus 1 times the thickness of this mica plate. So essentially what you need to find is, I guess, the thickness, which is basically of the mica plate. That will be x times d over d n minus 1. So you are given everything in terms of x is given, which is basically the shift in the central fringe, which is basically 0.2 centimeters. The d is given, which is approximately 50, I guess, 50 centimeters. This is d. And then the small d is given. What else is, and the refractive index is given. So you compute the thickness, so you get around roughly the value of 6.9 micrometers. So this particular thickness is 6.9 micrometers. And the important thing is that the thickness of this particular mica plate is 6.9 micrometers. So this is 6.9 micrometers. That is going to bring a shift of 0.2 centimeters. That's the essential concept of this question. And now there is a lot of interesting thing that is basically happening in this double slit experiment. So sorry, what is happening? So what happens if you have a, let's say, if you talk about what is basically happening in this double slit experiment, it's like the electromagnetic wave is coming like this, obviously in the form of a plane waves. I'm showing it in form of a waveform. The electromagnetic waves are coming like this, and they are interfering and they are giving rise to this particular diffraction pattern. It's a diffraction pattern because, or it's an interference pattern to be simplified, not to confuse you. So it's giving rise to this interference pattern. So what is exactly happening if you talk about in terms of the, I should say, waves? There is something called as, okay, let's not go into that detail because it will just complicate the process. This is the exact scenario for this question, because I don't want to go into the deeper aspects of this double slit experiment. And this particular double slit experiment has been even done for even if you have electrons, and if you fire the electrons one by one through these slits, you fire these electrons, what you're going to see is a distribution something similar to this. That means your maximum electrons will hit the screen here. It will be here at these particular positions, which again sounds bizarre because it also gives you an idea that electrons also act like a particle. They also act like a wave. But this is a famous experiment. It's called as Hitachi double slit experiment. And that basically proved the electrons to be also acting like a waves. But there are a lot of details about these particular experiments, which I don't want to go into this particular course because it's not a course for uh, quantum mechanical details. Otherwise, this is more goes into the quantum mechanics of the electromagnetic waves and also for the electrons. I don't want to discuss it. This is just from the classical perspective, from the wave nature, how basically the things are happening, that we basically understood from here and from the constructive and destructive interference. So this is it for this particular question. Now you have the Rayleigh range, which is basically I talked about in this particular I talked about here what Rayleigh range is. It's basically it's a range which the, let me show you what this question is. So the Rayleigh range, when we talk about the Rayleigh range, it characterizes how quickly the beam diverges as it propagates through the space. So essentially, when we talk about this beam waist, then there is certain range which is called as Rayleigh range, and it is basically defines the distance from this particular beam waist over which the cross section of basically doubles. So if this cross section was, let's say, W naught, then it defines the distance at which this W becomes 2W naught. So this is something called as Rayleigh range, at which the divergence becomes significant, and after this the divergence becomes huge. Up to this point, the beam waist becomes of the order of 2W naught. So that is how the Rayleigh range is defined. And in terms of the equations, the Rayleigh range we write in terms of similar to what we saw in this particular problem. We can write the divergence angle in terms of the wavelength and in terms of the uh, beam waist. So similarly, we can write the Rayleigh range in terms of the beam waist and in terms of the wavelength. And essentially, the Rayleigh range is inversely proportional to wavelength. That means if you have a larger wavelength, higher wavelength, the Rayleigh range drops. For smaller wavelength, the Rayleigh range increases. What does it mean? It means if you have a UV laser and if you have a IR laser, let's say around 1060 nanometers, and this is around, uh, let's say 300 nanometers. So Rayleigh range for here is going to be more, and here it's going to be less. Okay, that means the distance at which the it diverges will be more in case of UV compared to that of the I should say IR lasers. So this is the essential answer of this question. These are simple questions, but it's also directly proportional to the square of the beam waist. If you increase the beam waist, the Rayleigh range is gonna increase. That makes sense. If you shrink the beam waist, the Rayleigh range is also gonna reduce. Okay, so that's as simple as that. Now, the wave nature of light is demonstrated by, okay, this is again a very simple question. You know that if you have the light as a waves, then it can show the interference effects, it can show the diffraction effects. And essentially, these are the two answers of this question. And interference is basically you have a wave coming in, you have another wave, and you have another wave, and if these points are aligned, basically if they are in phase, then these points can basically add up and give rise to a constructive interference. On the other hand, if these points are misaligned, or these are, let's say, out of phase, so the peak of this falls on the uh, trough of this, and similarly, then this and this is going to cancel, this and this is going to add, this and this is going to cancel. So you have basically destructive interference. And this can only happen if you have the waves, not a particle. The constructive and destructive interference cannot happen with the particle. So that's why you talk about a wave and you talk about a particle. If we talk about electromagnetics, particularly, you have a wave, you have a particle, and you have when you talk about the electromagnetics in terms of the wave, so you have basically electromagnetic waves, and these are governed by Maxwell's equations. Whatever you saw, the del cross B, the del cross E, del dot B, del dot E, you have the electric field, magnetic fields, you have the propagation direction, the propagation constant, so on and so forth. So this is a typical wave, and you have constructive interference, you have destructive interference, you have diffraction, okay? And now what else is there? Now, if you treat this wave as a particle, then you have basically something called as a photon. A photon is basically a quasi-particle. It's not a particle, it's just the field is basically quantized. So once you go from electromagnetic waves to a photon, you have basically quantized the field. Okay, you arrive at a photon picture. And it's very, I should say, for this photon, you solve it in terms of I should say, operators now because it's a quantum mechanical entity, so you have operators. You have a field operator now. You have a field operator. Just like in quantum mechanics, if you have a distance in classical mechanics, you have a distance operator. If you have momentum in classical mechanics, you have a momentum operator. You have energy operator. Similarly, there are other operators, which is basically the field operator representation in the of the particles, and it goes into the domain of something called as quantum electrodynamics, and it goes into quantum optics, where the quantum nature of this particular light comes into picture, and you are treating this as a photon now instead of the electromagnetic waves. So this is now a single entity rather than a multiple number of photons altogether. And the essential thing is that how does it come into picture is because you have something called as quantization in the quantum mechanical picture or in terms of quantum electrodynamics. What is quantization? It's basically you have certain wave and you use some quantum mechanics and you quantize it to form a particle. That is exactly how the particle picture comes into the particle picture comes. And what that quantum mechanics is, that is very weird because what basically you have something called as first quantization, you have second quantization. So the first quantization is basically you are quantizing physical observables. Physical observables means your position, momentum, energy, okay? And the second quantization means you are quantizing the fields itself. Let's say you are quantizing the electromagnetic field. If you quantize electromagnetic field, you get a photon. You are quantizing acoustic waves. If you quantize the acoustic field, you get a phonon. You're quantizing, let's say, uh, maybe a spin wave. You have a spin waves of the electrons. If you quantize spin waves, you get a magnon. Okay, if you now have plasma waves, you have plasma waves of electrons. If you quantize it, you get a plasmon. So on and so forth. There are so many ons, and these all are basically quasi-particles. These are not exact particles, but these are used to understand the dynamics, quantum mechanical dynamics of these particular waves. So you go from wave nature to the particle nature. And what this second quantization is, what this first quantization, most of you might have seen, like going from X to X cap, which is basically the operator in the quantum mechanics. So you have momentum, you go from momentum to a momentum operator, which is basically I h bar dou by dou x, I h bar dou by dou y, I h bar dou by dou z. Essentially, you are solving the Schrodinger equation. You go from a single momentum to a momentum operator by solving the Schrodinger equation, and you get these operators. Similarly, you have energy operator, which is basically h bar square divided by 2m plus dou square over dou x square. Similarly, you have dou y square, dou z square. This is the energy operator. And this is basically quantizing physical variables, observables, not variables. Physical observables means these are actually measured in the experiments. You can physically observe them. You can measure the position, you can measure the momentum, you can measure the energy of the electron using certain experiments. And you are quantizing them, and that's called as first quantization. But if you are quantizing the fields itself, let's say the electromagnetic field, acoustic field, you're getting something which is called as a quasi-particle, and that's called as a photon, and the other is called as phonon, so on and so forth. And now what this second quantization is, it's not the topic of this particular course because it's not a quantum mechanical course, but the second quantization is basically quantized fields. So you have, let's say, this electromagnetic wave, and you apply certain certain rules which basically come under second quantization. It's again solving the Schrodinger equation. You have to basically solve the quantum harmonic oscillator problem. Instead of a simple harmonic oscillator in classical mechanics, you go to a quantum harmonic oscillator. And again, now you have all sorts of operators. you have the field operators. So everything becomes sort of quantized. And once you have a quantized picture, you get basically the energy of a energy in terms of the let's say you have let me give an example, simple example. You have a simple harmonic oscillator and you have a quantum harmonic oscillator. In the simple harmonic oscillator, let's say you have a spring and mass system, and you know the potential energy can be written as half of kx square, which is basically half of m omega square x square, where m is the mass of this, omega is the angular frequency, x is basically the displacement. Okay, this curve exactly looks like this. It's a parabola. Okay, it's continuous. That means the potential energy of this particular spring mass system is continuous. It doesn't take a discrete value. But if you go to quantum harmonic oscillator, and if you quantize this simple harmonic oscillator to a quantum, you make it as a quantum problem. You know what you get? You get a quantum harmonic oscillator. And what is a quantum harmonic oscillator? You have essentially the potential energy profile. This is like this. The potential energy is something, it's also parabolic, but there are discretized energies. And this is N1, this is N2, N3, N4, N5. And each of this energy is basically an energy level that can be taken by a quasi-particle. And when you quantize it using quantum mechanics, you get the energy which is exactly h bar omega n plus 1 by 2. So I don't want to show you how you get this energy, but you might know the energy of a photon is h bar omega. Okay, or energy of a photon is h nu. Okay, if you know this, then I mean it's not the exact same route how it comes, but when you use the quantum mechanics, you get the quantized energy of this oscillator is basically h bar omega, which is Planck's constant times the frequency, and n is here basically something called as number state. And in terms of the operators, you write it in terms of something called as a dagger and a. So n is basically a dagger a, and these are called as annihilation and creation operators. And again, it goes into the details. I don't want to discuss, it's already too much detail. And then you have basically these discretized energies, which is basically E1, E2, E3, E4, E5, so on and so forth. And now what happens is basically the particle is only able to take this energy, or this energy, or this energy, or this energy, or this energy, so on and so forth, depending on how higher in energy you go. So now instead of a continuous value, you have discretized this oscillator and you have discretized energy values. And now you talk about in terms of particle. Earlier, now you had a wave, but now you are talking about particle. Let's say you have a acoustic wave that is basically treated as spring mass system. So you have an atom, they are connected like springs, and you solve the same problem, simple harmonic oscillator, you get a potential energy profile. But if you quantized it, you get this quantized picture where the particles are basically taking a discretized values. So your particle can be here, 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 here. It cannot be in between. So it's basically quantizing the energies of the particle. Okay, altogether. So that is the essential concept of how the second quantization plays a key role in understanding the particle nature of these. Similarly, you have the spin waves. That means if you have an electron is having an upspin or it's having downspin. So in certain systems, if you align the upspin, and if you play with the spin of the electron and it looks something like this, maybe something like this. So you are basically orienting the spins in certain directions by using certain external fields. So essentially what you have done is that you have formed sort of a wave, and this is called a spin wave. And if you quantize this spin wave, you get a quasi-particle, which is called as magnon. It comes from magnet basically because spin is related to magnetic field. So you have got a magnon now. You have a particle which is actually propagating from this direction to this direction. But it's not an actual particle, it's a hypothetical particle. But it's as if the motion is occurring because of particle. Otherwise, it's actually a wave. So that's the essential concept of these. Just like the phonons are basically the atomic displacements. So essentially, if you compress the atoms here, it's gonna come closer here, it's gonna come here. The atoms are gonna displace in this direction. But once they displace, it forms like a wave pattern. And then you quantize this wave, you get when you quantize it, you get a quasi-particle. You treat it as a phonon, and you think that as if it's a phonon moving in this direction, not a wave. So that is essentially the idea. And now you can understand why this is important is because this quasi-particle can now interact with the electrons also. And this is something goes into now the electron phonon interaction. So that is why all of these fields are important. The wave nature, the particle nature, the the interference, the diffraction, the quantization of it, and the the understanding the second quantization, the quantum harmonic oscillator, simple harmonic oscillator, and how these phonons can interact with the electrons in changing their energy. This is all related in electronics, semiconductors, photonics. So that's why this is such a huge field. Okay, and this is too much detail for this particular question because these are just simplistic questions. You don't want to just tick mark them and then just move to the next question. Doesn't make any sense. Now, in a wireless channel modeling, this is a different question altogether. Let's go back to the wireless channel modeling. And essentially, you have basically a wireless system, which is basically if you follow something called as two-ray ground reflection model, you might have seen in the lectures, two-ray ground reflection model. In it, basically, you what you treat is that the waves are moving like on the from one region to another region in free space, and they are also moving in this direction, and then they get reflected. So this is basically called as two-ray model. So there's a ground reflection from here. This is the ground. So the one of the component is going like this, other components are going to the ground, and they are reflected from the ground and reaching the receiver. This is the transmitter. And what is basically important is essentially to understand that the the power you need to understand what happens to the power at let me just give me a moment. I'll just reconnect the microphone. Yeah, so essentially what is happening basically, you're treating this as what basically we need to see is that the power after the breakdown point drops to what value. So what this breakdown point is basically referred to. So you know that because these are moving as waves, so these are also moving as waves, and this is a moving as a wave. Because of this motion, just like I talked about in double slit experiment also, because it has to take a longer path, and that adds a path difference, and that path difference manifests as a phase. Okay, so if your wave is going from this point to this point, it's traveling distance, let's say x1, and if it is going like this, it's traveling distance x2, and it's reaching the receiver, it's covering distance x3. So essentially it's covering a lot of distance here, x2 plus x3, which is certainly greater than x1. Okay, so let's say this is transmitter, this is receiver, and additional whatever the additional path difference is basically here, that is gets that is basically seen in the phases of this particular wave. Additional path difference is basically associated with the phase difference of the wave. So let's say you have a sine omega t. This is the normal. Let's say that you have sine omega t here. Then essentially here at this point you will be having sine omega t plus phi. Okay, and this phi will be related to the path difference, related to x1 by some relation. Okay, so the path difference is associated with the phase difference. And why is it necessary? Because essentially these are waves and they are getting reflected. And once the wave is getting reflected at this point, there will be phase change also. And that phase change also adds up. Now we need to find a certain distance at which the something called as the behavior of this received power changes. So if you are receiving the power at this particular point and at this particular point, you will be having two different scenarios of the received power. So essentially, your uh, received power behavior is going to change depending upon where you exactly measure it. Okay, because of the reflections. It's as simple if you are walking down the lane and if you have houses here and if you have houses also here and if you are walking somewhere like this and if the mobile base station is located somewhere far away, then you're basically in a certain region which is basically a sort of it is enclosed region sort of, and the waves have to basically come to your mobile phone by reflecting from these structures and then are received to your mobile phone. And at some point you might see that the signal intensity completely drops, decays. That is exactly what is meant by this behavioral change of the electromagnetic waves. And because these electromagnetic waves undergo reflections, okay, and we need to find this because if the destructive interference occurs between a direct wave and a ground wave, then your received power is gonna reduce significantly compared to the constructive interference. So it's all about interference phenomena. And if you say that you are basically what is called as the distance at which the power received power transitions uh, is basically dependent on it depends upon the distance between these particular two sources. That means the transmitter and the receiver. So if you have, let's say this is a breakpoint, let's say this is a breakpoint, let's call it X, then essentially the if you are receiving power here, your received power will be inversely proportional to d square. That is a simple power relation. It varies as a distance square. But after the breakpoint, it varies as inverse of distance to the power 4. That means it drops more significantly after it. That means if d increases now, your power is going to reduce by 4 times. I mean, your power is going to drastically reduce after this particular breakpoint. So that is why if you now convert this particular relation, your power is varying as distance to the power 4. You're going to convert it into logarithmic scale. You write it as 10 log to the base 10, 1 over d to the power 4. You get approximately minus 40 log to the base 10 times d. This will be exactly the scenario. So the slope is exactly, or slope, whatever you call it, it's exactly becoming minus 40 times, minus 40 decibels per decade, basically. Okay, so this is the exact scenario. That means after it, what is basically happening? If you talk about in terms of the power scenario, that means after the breakpoint, let's say this was the breakpoint. Here the power is varying as 1 by d square. Here the power is varying as 1 by d4. After the breakpoint, you have minus 40 dB per decade of loss. And here you have minus 20 dB per decade of loss. What does it mean? It means if you draw power in decibels, it's just a unit to compare the two power levels. And if you draw with respect to, uh, let's say, let's say if you had a power of obviously with respect to the distance, that means per decade change of a distance. Let's say this is in meters. For just an example, let's say this was 10, this is 100, and this is 1000, this is 10,000, so on and so forth. And let's assume this was the breakpoint. Let's assume this was the breakpoint distance. So let's say your power was, let's say 60 dB. I'm just giving you an example. 40 dB, 20 dB, 0 dB, and then you have negative 20 dB, negative 40 dB, so on and so forth. Assuming these are just examples, this is just an example I'm showing, not the exact power levels. Most of the time it will be below zero, but it is an example. So if your power level at the particular point, this is the transmitter position and this is the receiver position, and this is here you are placing another receiver at the break point, basically at the break point. Okay, so essentially what is basically happening, you are up to the break point, your power is varying as minus 20 dB per decade slope. That means if your power at this point was 40, at the break point, it's gonna be 20. This is minus 20 decibels per decade. Per decade means every 10 change. Okay. And now after this, the power level is gonna drop to significantly. So slope is gonna change. It's gonna reach to minus 40 decibels per decade change. So this is the exact scenario. So this slope, the point at which the slope of this power changes is significantly is something referred to as the breakpoint of in the wireless transmission. And the signal intensity drops significantly beyond this breakpoint. So that's the essential concept of this particular question. And that means this is the answer of this question. Now another question, which is basically what's the time? What's the time? Question 7, question 8, question 9, question 10. I guess they are related. So if you have a rectangular aperture with a transmittance function, you have an aperture and you are irradiating certain light to it. So you need to basically find what will be the diffraction pattern formed. So you know the light is going to spread and you're going to get certain pattern here, whatever the pattern is, based on how the light is spreading. Okay, how the light is spreading, you're going to go get some pattern here. That will be basically the diffraction pattern. So it's as if you have a rectangle, a frame, and you're shining it with light. You're going to get some shape here. It depends. So these edges can be blurred because the light is getting diffracted at this particular eye and the light is getting spreaded. It depends upon how the light behaves. Mathematically, what is happening? So that is basically this question is this question is about. So you are given amplitude transmittance function of the light. That means whatever is basically transmitting, you are given it in the form of a mathematical function in xy coordinates, and that is rectangular function of x naught divided by 2wx, rectangular function of y naught divided by 2wy. Let's try to understand this question. Oh no, not this thing. I need this. Copy, paste. Question 7. So basically what is happening? You have a rectangular aperture, which is basically represented as a mathematical function. Obviously, when the light will pass through a rectangular aperture, it will behave as this particular function. How this function looks like in the xy, if it's really difficult to make because it's a two-dimensional. Not exactly difficult, but if this is x, this is y, and this is TA x naught y naught. This is x naught. This is y. This is x. No, this is xy. This is TA x comma y. So it's a three-dimensional function, obviously. Because there are xy, then you're plotting TA xy as a function of x and y. So it's gonna look like not this. It's a rectangular function. Yup. Yeah. So this is exactly how it looks. So it's a rectangular function where this width is basically wx, this width is wy, and this is basically the mathematical function you're given. and the light is passed through this particular function. What happens to the light? The essential point is that when the light encounters any of the object, in order to in order to basically map this object and get its image over here, the light has to interact with this object and it has to interact at different locations. Let's say a light interacts with the edges of it and it got scattered from the edges and that light reaches here. This light got scattered from the edge and it reaches here. Some of the light went through it here. Some of the light is coming here, coming here. Now, when will be the light able to perfectly capture this particular object? That's the question. That is where essential concept of Fourier transform comes into picture. And I've been focusing on this topic a lot in the previous sessions. I told you in the first slide also that when you talk about Fourier transform, you're talking about time to frequency transform. That means you're going from a second to per second. That means hertz. And you have one more Fourier transform, which is basically called a spatial Fourier transform, a space Fourier transform. That means you're going from a real space to inverse space. That means you're going from meter to inverse meter. This is called as spatial Fourier transform. That is what exactly happens when you want to image any of the object using the light. It happens in cameras, it happens in optics, it happens in everything you are seeing around you. Now, what is the essential concept is basically if you want to image this particular object, you want to create its image over here. So these sharp ends of the object, these represent the high frequency parts of the object in the K space. In the real space, if it is let's say because this is in real space, but then you have to convert it into some K space form, which is it's sort of a mathematical representation, but you want to understand its frequencies in space, how the light will behave with these particular edges, but what sort of frequencies does these edges carry in real space? Just like these, not only edges, the entire object, just like this object is having like this. So these edges require very high frequency to essentially create an image of these. Apart from this particular ends, which do not require high frequency to interact. That means if you have a light wave which is having a frequency like this, it's going to perfectly replicate these particular parts. But if you have these edges, you're going to require very high frequency light to interact with it so that it can perfectly capture these particular edges. Okay. And on the other hand, if you just deform this object, if you change its shape to something like maybe you make the edges round, something like this. Now the scenario changes. Now in order to capture these edges, you don't need the high frequency all because these are not high frequency informations. You can have a light that can interact with it and it's going to replicate it really sort of a easy peasy way. It doesn't require high frequency because it doesn't carry high frequency information at these edges. So the sharper the object is, difficult it is to perfectly capture in K space or to form its image. That is the perfect exact concept. And where does it come from? It comes from the exact Fourier transform. Because if you have certain sharp features in real space, okay, in inverse space, it's gonna have a huge, very high frequencies. Why? Because if you have very small object in X in real space, it will be let's say it will be 1 nanometer. But when you are gonna image this small object in the K space, its its sort of transformed version will become 10 to the power 9 per meter. So it will be having high frequency components. However, it will represent, that's not your concern right now. But in the K space, its constituents will be having huge frequencies. Apart from if you have a large object, then to image it, it's going to have low frequency components in the K space. That's exactly what happens in your cameras or your basically all of the optics you're talking about, even the microscopes. If you have a very small feature, it has very high frequency in K space. I'm not talking of high frequency in from time to frequency. I'm talking about high K values, high wave vectors, or the high frequencies in the K space. Okay, compared to if you have a larger object, you have lower frequencies, and it becomes easier to visualize those objects. I'm talking about really in terms of a layman picture, because if I complicate it, then you're gonna get confused. That is why it becomes really difficult also to image smaller objects because they carry higher spatial frequency. Okay, that is the concept of spatial frequency. And one of the essential thing is now, if you wanna, what was the question? The question was that the Fraunhofer diffraction pattern seen is, so Fraunhofer diffraction pattern is exactly that you are illuminating the light through this, and you're gonna see certain diffraction pattern, which will be exactly the Fourier transform of this. But in real space, it's a real space to K space Fourier transform. Okay, so that means you're gonna Fourier transform the TA of x naught y naught function, and you know that if you have a rectangular function, if its Fourier transform is sinc function, so essentially the answer will be sinc. So that means your the function will look something like sinc of 2wxx divided by let's say kz into sinc of 2wyy divided by kz, essentially in terms of what it is given. Yeah, it's given in terms of yeah, it's just a wave vector. Doesn't matter. Yeah, okay. So this is just the Fourier transform of these particular constituents. So if you have a let's say let's say I draw it separately. This is x and this is y. So this is a rectangular function of x naught 2wx, rectangular function of y naught 2wy. You Fourier transform it, you get a sinc function. Why did I write sine? This is sinc. You get a sinc function in K space, and how it's gonna look? It's gonna look something like essential. It will be easy to draw it here because they are exactly centered around origin. Yeah, so it'll be rectangular functions because you see this is rectangular function of x naught divided by uh, x naught divided by 2wx. So if it was x naught minus some other value, then we could have centered. We can center them around origin. This is 2wx. This is 2wy. So it'll make our life easier. So essentially, when you Fourier transform this from x to k space, you're gonna get a sinc function. Similarly, a sinc function here. Oh God, sinc function. This is exact exactly how it looks. I have shown it separately. We can show it in a combined form basically. That means what has happened is that this particular rectangular whatever the rectangular frame was given for the diffraction pattern through which the light is basically passed in the frequency representation in K space, it's gonna look like a sinc function. It's gonna be more sort of localized. That means this is if this was spread, this is basically more localized. These are diffraction patterns coming from it. The essential lobe is main lobe is this. These are diffraction. Uh, I should say higher order diffractions. Higher order diffractions. Similarly, these are higher order diffractions. This one, this one. This is the main uh, first order diffraction that comes from it because of the Fourier transform. So now if you go on increasing the width of this lobe, what you see is that this will shrink. It will become like this. So the higher you will make this object in the X space, the localized this will become in the K space. And what does it exactly mean? It means you will have exactly the information of this particular object in the K space or the frequency representation. And this is exactly what happens with the signals. If you have a signal that looks like if you have a sinusoidal signal that is going from minus infinity to plus infinity, minus infinity to plus infinity, what is its Fourier transform? Is sort of a delta function, x minus x naught. Let's say this is x naught. Okay, but if you truncate the signal, if you remove this part of the signal, now your signal only starts from 0. It goes from 0 to plus infinity. When you Fourier transform it, what do you see? You see that this delta function has a spread now. Okay, and this is a spread of this delta function now. Okay, now again what you do, and why does this happen basically? Because when it spreads, earlier it was peaking only around single value, which is x naught. Now it has a spread. That means it has all other values in it. It has this value, this, all other values, and it's peaking around a central value. Where does all these values come from? Where do they come from? They basically come because you have removed this part of the wave, and in order to mathematically remove this part of a wave, you need to essentially have interfere lot of waves with it so that it will cancel this part of a wave and it looks flat here. So essentially you had a waveform like this, but mathematically what you are doing is you are supplying it with so many waveforms now so that they all cancel each other, and now the only remaining wave is basically this, and whatever the waves you supply to cancel these waves on the negative end, they are basically coming reflected in the Fourier transform as these particular components. That's why it has now a spread. Earlier it was peaking around a single point, now it's spreaded. Now essentially what you do, if you now again truncate, earlier it was from 0 to plus infinity, you again truncate this part. You make it time limited. It's now a time limited signal going from, let's say, 0 to t, some t, time t. Now again you see what you see. You see a spread of this particular in the Fourier transform domain. You see a spread which is peaking around certain frequency, omega naught. Okay, so omega naught is exactly related to the time period of this signal, which will be the time period. And then there are these other components of the in the frequency domain. Where does those components come from? Because you have cancelled these particular frequencies, you have cancelled this particular waves, and all of these waves are now reflected in these other components mathematically. That's what is mathematically happening. Because you cannot mathematically have a time limited signal. Whenever you do the Fourier transform, remember you write the Fourier transform if you have a function, you want to go from f of x to f of x to f of let's say f of k, or let's say you're familiar more with the f of, you want to go from a function of time to a function of frequency. Remember how you used to go? You used to write the function of frequency in the Fourier domain as 1 over 2 pi minus infinity to plus infinity, and you have f of t e to the power minus j I omega t into dt. So this is how you used to write. And essentially, you are basically summing up all of the waves, which is because of this factor. E to the power minus I omega t is basically all of the waves from minus infinity to plus infinity. You are adding up, subtracting them, and comparing with the function. And all of those are basically coming up in the frequency domain. That's why when you truncate the signal, all of those signals that you are truncating appears in the frequency domain. And that's why the frequency domain is essential because it gives you the information which all other frequencies were present in your signal and what exactly your signal looks like. So this is exactly how mathematically it looks like. Now, essentially, what is basically happening if you now have a this was in time to frequency. This was time to frequency. Now, if you go from space or a real space to inverse space representation, and that means essentially if you have an object which just looks like this, which is with a rectangular function, it was having a sinc function like this in the inverse space representation. If you go on shrinking this object, you're gonna make it like this. You're gonna have a representation which looks like this. You're gonna shrink it more. You're gonna have something like this. And you're gonna shrink it more. You're gonna make it smaller and smaller in real space. You in frequency space, you're gonna have a huge spread of this particular function. So that's exactly the concept. So it determines uh, how your object is basically behaving, and that is why it is necessary for the image processing point of view because the smaller you make this particular object, the essentially to map these particular ends, it's gonna because it contains high frequency components, it's gonna take a lot of waves to exactly map these particular edges. Okay, so that's why you would have a lot of high frequency components if you want to map these particular edges. And you can also, if you're interested, you can look at its I should say application in the image reconstructions. Whenever you are reconstructing any image, satellite image, mobile phone image, or any of the image, you're going to see its application, how basically an object is reconstructed. Let's say you have a human standing here, and you're taking a picture with your mobile phone camera. Essentially, what is happening is that the photons are hitting the human, those photons are entering the mobile phone, but the human body contains different frequency informations. Let's say if the photon is coming from the head, then it requires the head is containing low frequency information essentially in real space because it's sort of a circular, it doesn't have sharp edges. But if it's coming from something like hands, it needs very high frequency components to basically resolve this image. So it needs high frequency components. Similarly, the other hand. That's why you see that if some objects are very smoother in real space, they appear smoother in the pictures as well. But if they are having very sharp edges, then they appear blurred in the image. Why do they blur? Because to image these particular ends, they are high frequency informations. And to map those high frequency information, it takes a lot of effort from the image construction point of view. And that again now goes from X to K spaced Fourier transform. And that again boils down to these particular Fourier transforms, which is basically the backbone of these image reconstruction techniques. So essentially, the essential concept of this is that it is going to be proportional to the sinc. And if you want to measure the intensity, that will be proportional to the sinc square, basically, not only the sinc. But here it's asking for the normal. It's asking for the unit amplitude for an upper diffraction pattern seen. Okay, it's asking for the normal amplitude. But if you want intensity, then it'll be sinc square. But it's not asking for this intensity. It's asking for the amplitude. Now, from the information, the intensity along x will be 0 at. So we need to find at what point the intensity will be 0 because now you have a diffraction pattern formed and you see that you had an object like this, you've shined some light, you get a diffraction pattern. So So the object was looking like this, but in a frequency representation, the object is basically looking something like this. And you see that these lobes, which are diffraction lobes, where they are coming from, they are coming from edges. Okay, they're coming from these edges. The middle part of it is fine. I mean, it's mapped to this particular lobe, but the edges are mapped to these diffraction patterns because the edges are the ones that diffract the light, that cause the diffraction or scattering of the light or spreading of the light. So that's why again it boils down to this fact that these edges are the diffracted or the high frequency components of this particular object. And the smoother you make these edges, the better your image will be basically in the frequency representation or essentially your image. Now, what is basically happening? That means you are having these nodes and you are having this antinode. I'm talking about this is basically an antinode. This is a no, this is an antinode. This is a node at which the intensity is dropping to zero. It's reducing significantly, and at this point intensity is maximum. So you are asked in this question that the intensity along x-axis will be zero at what point the intensity will be zero exactly in this particular question. So when you look back at this particular question, you need to find at what point the intensity will be zero. So you are again going down to the same equation. You are given Wx is 0.005 centimeters, which is basically this spread in the real space. You are given Z as 100 centimeters. Lambda is given as wavelength as 5 into 10 to the power minus 5 per centimeter. And this essentially, let me just check. Yeah, this is okay, yeah. So what happens is now in the diffraction pattern, you know that these intensities fall to zero at some integer multiples of the pi because at the end it's a sinc function. Now, if you have a sinc function, you can basically have that the intensity falls to zero at whenever this that means the sinc function of what was the sinc function 2wx over lambda times z. By the way, this is wavelength times the z-axis. It's not lambda z, it's wavelength times z. So it should go to exactly zero. It goes to zero when this is basically a multiple of some integer multiple of pi. Okay, so that means it is basically 2wx divided by lambda z with integer multiple of pi and pi. So essentially for m equals to 1 for the first diffraction pattern to go to 0, for the first lobe, it goes to 0. We need to find x, that will be lambda times z divided by 2wx, and this will come out to be equal to 0.5 centimeters. So that means it will go 0 at 0.5 centimeters. Okay, so the answer of this particular question is B. And if you want to have the other condition is that when this point will be maximum, it will be maximum at m plus 1 by 2 times pi, which is basically the odd pi or the I should say not the integer but or the odd pi. It will go to 0. This is basically the integer pi, and now the answer for this is 0.5. And now again the same question, the grating aperture with transmittance. So this is a different question but a little bit complicated. The width and fs is the spatial frequency of the grating. If this grating is illuminated with unit amplitude, normal, incident, monochromatic, the front of a diffraction pattern will be. It's again simpler. So it's saying that we have to consider grating aperture. Grating aperture looks something like this. Grating means you have sort of apertures like this. It's called as grating. And it has an amplitude transmittance function given by this mathematical function. The only difference here is there is some cost term. Okay. And a cost term in only x direction, not in the y direction. This is really important. You can just plot it also. And essentially, it is basically half of rectangular function of x naught divided by 2w, rectangular function of y naught divided by 2w, plus half of cos of 2 pi fs x naught, rectangular function of x naught divided by w, rectangular function of y naught divided by w. So basically, these are two different functions. That's why it's forming a grating. It's sort of this, then this. That's why there are two functions. And there's a cosine term which is basically which represents the spatial frequency of the grating. What is spatial frequencies? If this is grating, that means these are different. Uh, I should say this consider it this is an object which is basically having certain staircase like a formation, serpentine pattern, or rather the staircase type of a pattern. Then essentially this cos takes into consideration the spatial frequency of this grating. What is spatial frequency? It is the frequency at which these gratings are repeating. This is the spatial frequency. At what frequency these lines are repeating in a real space is basically spatial frequency of this particular grating. Okay. So if this grating is illuminated with a unit amplitude, normally incident monochromatic wave. So you have a monochromatic wave that is coming in and it's getting diffracted. Obviously, now you have to find the diffraction pattern of TA1 grating is. So you have to find the diffraction pattern of the first grating. So essentially these are two gratings, TA1 and TA2. That's what basically the question is. So you don't need to consider the overall function. So what basically question says, you have two set of repeating gratings. So you have repeated gratings with TA1 and TA2, and the spatial frequency is something given in the question. And this TA1 is having a function of half plus half of cosine of 2 pi f x naught. And this TA2 is having a mathematical function of rectangular function that is basically given, two rectangular functions, okay, in x and y. Now you need to find the Fraunhofer diffraction pattern of only first grating. What happens because of this grating? Essentially, you need to basically Fourier transform it. So if you have a TA2 first, you Fourier transform it, you again get the sinc function, similar to previous. And if you have now the sine function, which is basically not the sine function, the cosine function, which is basically TA1, you have to Fourier transform it. You know the cosine's Fourier transform is delta function because it's cosine of 2 pi fs x naught. So you Fourier transform it, you get half of delta function of fx plus fs y plus delta function of fx minus fs y, and essentially now what you have is the Fourier transform is in the form of delta function. Yep. So it will be fx fs plus fy. This is fx plus fy, fx half 1 by 4 fx plus fy, and 1 by 4 fx minus fy. So you have fx plus fy, fx minus fy. So basically, if you have a cosine function, you have in the frequency domain, you basically have main component and you have sidebands, which is omega minus omega s, omega plus omega s. This is exactly what it represents. Then why is this not, where did this component come from? Okay, so Yeah, that can be understood from this also. Or I think the best way to solve it is if you have a cosine function which you can write something like this, then you can essentially write it in terms of exponential function, which will be e to the power some. Uh, I'm hating this. Let's write it as omega s. You can write it as e to the power j, maybe omega s x naught plus e to the power minus j omega s x naught divided by 2. And then you can basically Fourier transform it. You can get 1 by 2 plus 1 by 4 e to the power j omega s x naught plus 1 by 4 e to the power minus j omega s x naught, and not the Fourier transform, just taking out the components, because you have 1 by 2 plus 1 by 2 cos of omega s x naught. So you have 1 by 2 plus 1 by 4, then exponential plus 1 by 4, and then exponential. So this is exactly the terms. Then you Fourier transform each of this term. You Fourier transform this term, you get f of or f for omega x. Omega s x minus omega s comma omega y, and here you get omega x plus omega s comma omega y, and you have here 1 by 2, you have 1 by 4, you have 1 by 4, and this should be like this. So essentially you have to compute the Fourier transform. So the one that's matching is this particular option. As simple as that. I just complicated it. Simple. So that's how you can compute the Fourier transform of it. And again, if you want to compute the diffraction pattern of TA, then you have to compute basically the Fourier transform of the other amplitude function. And this is a sort of grating which is bounded by a square aperture now, rather than a cosine. So the Fourier transform will be a sinc function, obviously, and okay, this is done. The question is asking what is the Fourier transform of what is the Fraunhofer pattern, overall Fraunhofer pattern. That means you need to find the overall Fraunhofer pattern. That means TA should be equal to TA1 into TA2. Okay, so essentially this is TA x naught y naught equals to TA1 into TA2. Okay, what you do is that you have already computed the Fourier transform of TA1. You compute the Fourier transform of TA2 also, which already you have, which is in the form of sinc functions. You computed in the previous question. Then, because uh, there is a multiplication here in the, I should say, real space, it will be convolution in the frequency space. That's what I am thinking about it. Let me just see. This will come only because of convolution, otherwise it doesn't make sense. Because there's a multiplication in this real space. So when you write it in terms of a frequency space, in terms of TA, the frequency space, whatever it is, omega x, omega y, it will be basically TA convolution with TA2. So this will be exact. And if you convolute sinc function with the sinc function, you again get the similar functions. Just like you convolute two rectangular functions, you get the function back. This convolution of sinc with the sinc is itself the function. And now what you will do is you will Fourier transform and you will convolve the results. And essentially you should get it in terms of sinc everything. And we still think if it is the correct way to do it. Mm, so you have the sinc functions. Yeah. Mm, let's just do it. I want to do it. I'm not sure if we get it. So if we had TA what was this TA1 what we got? Oh god, I hate going back. This is or delta function of f of x, f of y, f of x, f of s, f of x minus f of s. Let's write first TA2. I remember TA2 was something like rectangular function of x naught divided by 2w, which is basically x, right? Rectangular function of y naught divided by 2wy, and you compute its Fourier transform, you get sinc function of 2w 2w f of x or omega x, whatever you call it, sinc function of 2w f of y, and now you compute ta1 dot ta2. That means you multiply that 1 by 2, whatever was the function. What was it? This function, copy, paste. You multiply this function with ta2. Okay. So if you just simply multiply, you cannot multiply it in frequency domain. It should be convolution. Yeah. So, or either there is one more way that you multiply it in space domain only, and then take the Fourier transform of that, and then essentially that will give you the exact answer. But the simplistic way is to just, when you don't want to convolve, I just want to find the simplistic way. hmm Yes, pseudo Fourier transform, and yes, I think that will be, yeah, I think this will be simplistic. And just to use the convolution, because it will just shift the sinc functions by this delta. So if you have a sinc function and if you have a delta functions, okay, it's gonna just shift it to this, let's say omega x minus omega s. It's gonna shift the sinc to this omega x minus omega s. That is as simple as that, yeah. So essentially you will be having some sinc function of 2w fx plus fs, and you will be having sinc function of 2w fx minus fs, and because it's only shifting the x, it's not shifting the y, there will be sinc function of 2w fy will still remain there, sinc function of 2w fy will still remain there, and then there will be, yeah, the amplitudes of it, 1 by 4, 1 by 4, and then there is the first part itself, which is easy, which is 1 by 2 sinc function of 2wfx as it is. It's not going to change. 2wfy. This should look something like this, the solution, because the convolution is just going to shift it. It's not going to cause any significant change. So it'll be 1 by 4 sinc, 1 by 4 sinc, and only the x component is going to change, because your original t1 ta1 function was only a function of x. Okay, and so you take the components back. Yeah, it looks like this: fx plus fs, fx minus fs, and this should be the answer. And that means you have to take one of the components common. Yeah, you can take here f of y common. You take f of y common, and you get it as this particular answer. Is it? No, because it's shifting y. It should shift x. This is y. Y, you took the y component common. You are shifting the x components. Everything looks similar. So this is the exact answer of this question. Yeah. Whew. Okay. Makes sense. So essentially this shift is coming because of the cosine term, because cosine is 2 pi fs x naught. That's the similar shift here, because now we have convolved. And this part will remain as such, just there is 1 by 2 term in front, which is because of the first term. So this should be the answer of this question. Yeah. So this is the exact answer of this question. Oh, I think I took a lot of time today. And we're pretty much done with this session, and pretty much with this course itself. And there will be one additional session, I guess, I believe next week, I should say coming week, Tuesday at around, if I remember correctly, it is around 3 p.m. I don't exactly remember, I have to see. But this is the final session of this particular course. I hope you can go through these lectures and at least gain some certain insights about the electromagnetics. Thank you for attending the lectures. See you soon in the next lecture, the final one, and it will be just a revision of all of the concepts. Okay, bye bye.